Okay, good. Okay. So yeah, let's discuss today's problems, which were Northeastern European regional contest, next stage of the ACM in Russia. After it followed the contest basically that you were following, that you were solving yesterday. So it was harder. And if you are looking to solve hard problems, you should take a look at other years of Northern Europe, Northeastern, especially last years. They're usually quite hard. So, okay. By the way, I found the statements outside just lying on the table, so if that's yours, you may get it. Okay. So the first problem was about, again, three-dimensional geometry, our favorite topic, which was you had a certain convex body in three-dimensional space, and your problem was to find the area of several cross-sections by several planes here. And well, that was it. You had up to 100 vertices of the body, and also you had to find the area 100 times for different planes. So okay, how do we solve this problem? Okay, let's consider a cut with a plane here. So if the body that we have is convex, then if we look at the cross section, then what we will have is a convex polygon, right? That seems about right. Something like this. Okay. The first question is how do we work with the fact that we have do something in three-dimensional space, but if you see, then our problem is actually that is finding the area is actually quite a two-dimensional problem, because everything happens in the plane. So if we were to find the vertices of this convex polygon, which is the cross section, we would just calculate the area just as we do in the plane, right? So the only problem is to find these vertices. And okay, how do we find the vertices if we have only the vertices of the convex body? So you have to think about what the vertices are, and the vertices are the points of intersection of these edges of the convex body with the plane. Okay, so what we could do is to try and intersect all edges of the convex body with the plane, and that's how we obtain the points, right? But the thing is, we are only given the vertices, so we don't exactly have the edges. So we could try and go and reconstruct the edges, but there is a simpler way to do that, because so an edge is a segment, right? Because it connects to vertices. Okay, so how do we distinguish an edge from a non-edge? Because there are some pairs that form an edge, and there are some pairs so that the segment is strictly inside the convex body, so that it's not an edge. The thing is, we don't exactly care. We can ignore that issue, because okay, if we take this plane and if we try some pairs of points and find the intersection of the segment with the plane, which is not too hard to do, because we know that when we travel from one point to another, then all the coordinates change in a linear fashion, right? because it's a line segment. So basically, if we have something like a point here and a point here, then the segment can be parameterized by x1 plus the difference, and the same thing for other coordinates. Okay, and the segment. So if we parameterize it with t, then t should lie between 0 and 1. Right? So as we gradually change t, we obtain all points in the segment. So to find the intersection point in the plane, we have to solve this for t, and the solution, the z coordinate here is equal to the z coordinate of the plane. So after we find t, we have all the coordinates. Okay, so that's intersecting the segment with the plane is easy, and you don't have to do much. So okay, we obtain a bunch of points here. And what we are going to do is we are going to take every pair of points here, every pair of vertices, and try and intersect the corresponding segment with the plane. Okay. So some of the segments do not intersect the plane. That's okay. We're just going to ignore them. So we have a bunch of points here. So some of them are vertices, probably, and the important thing is all the vertices are going to be here in our set, because every vertex here is the intersection of some segment with the plane. And we also have a bunch of points that are not vertices, but that's okay, since we can see that all these points are going to be inside the polygon, right? So what we are going to do now is how do we extract the vertices from here, and we extract the vertices just by building a two-dimensional convex hull of all these points. Okay. So, since our body is convex, that makes our problem much simpler, because like we don't care. We just construct the convex hull, and that's the correct intersection. Okay. So the problem boils down to having these planes. For each plane, we construct this set of points, and then we apply the two-dimensional convex hull. So the problem is not really three-dimensional, in fact. And you kind of have to be careful to get all the points of intersection right, because some of the points may be exactly on the plane, and you have to include them, some of the vertices. And well, if you go on and construct the convex hull, and then there can be some degenerate cases, like the intersection is a single line, or this convex hull is going to be a segment, right? Or there could be no points, or there could be repeating points. So you have to make the convex hull, your algorithm, robust to all these degeneracies. But other than that, it's pretty much standard convex hull task. Okay. Are there any questions about that? Yes. Maybe. It's hard to tell, really. It looks like. Well, maybe it's a different body then. I can't really tell. I don't know. The first one looks correct. It looks like a square. I mean, did anyone else had this issue that something didn't work on the samples? Maybe, I don't know. My guess would be that you miscalculated somewhere. Everyone makes mistakes, so that's okay. Okay, any more questions about that problem? The problem B was an interactive problem, and I don't know if you get to solve a lot of interactive problems, or do you usually have them in like Latin American competitions? No. So I was gonna say that it's like a recent development, but it's at least 10 years. So I think there were like cut-forces round with interactive problems some time ago in educational rounds with interactive problems. So I don't know if they were ever the world finals. My guess it would be no. So anyway, this is not too different from a regular problem. I think you eventually. I hope you eventually made your way through this problem, since it's not too hard of an example. You had a maze which you did not know, and you had to basically traverse through the maze blindly by sending commands like where do you want to go, in which direction, and you received answers. Either you could go there or you could not, and you had to visit everything and then said that okay, I visit everything. So if you had a maze like given to you, how would you construct the route? You would probably run a GFS, right? So this is what the solution to this problem is. Basically, you are standing in a maze which is large enough to like accommodate all possible mazes that could happen, and I believe there are at most, so all dimensions were at most 30. So if you consider everything with respect to your initial position, then the maze is bound to fit within the rectangle like 60 by 60, right? The square. So what you're doing is that, so you're standing in an initial square, so you know that it's empty, and for all other squares you do not know nothing basically. So all of other are question marks. And what you're going to do is to replace these question marks with some verified information. So for example, to verify this square, you want to basically go north, and then you know what this square is. So if it's blocked, then it's blocked, you know it, and you stay in the same cell. If you go, for example, to the west, then you may discover that it's an empty cell. So your goal is for every, if you have a bunch of empty squares, then you want to discover the state of all of its neighbors, and once you know everything about all the neighbors of all empty cells, that means you must have visited everything, right? Because if there is at least, well, there cannot be another empty cell, because it would be adjacent to basically another empty cell and so on. So when you've discovered everything about all the neighbors of the empty cells, then you must have the region of empty cells like bounded by the blocked cells. Okay, so the algorithm is to basically you have a bunch of empty squares, and you have a set of squares you want to obtain the information about, so that the question marks that are adjacent to some empty cells. So, and you know your current position here. So what you want to do is you take a particular question mark, and then you make your way so that to discover what is in the question mark. Okay, and to do that, you just make your way through the known portion of the maze. And well, since it's always connected, you can always make your way there, and that's how you discover a new cell. Okay, so basically you want to maintain a queue of question marks that you want to discover something about, and then you just process it and move it through the known part to the question mark, and then the next one. And if you discover that something is an empty cell, then that raises more questions. Like here, for example, if you go here, then we have these three new cells that you want to know about. Okay, so this is much like a DFS, except that in an interactive context, you get things as you go. But other than that, it's not different. Are there any more questions about this problem? Since this is a special, like, interactive problem, you have to write a program that outputs something that flashes its input and then reads something from another program that's an interactor program prepared by jury. So yeah, that's really the only thing that's different. You have to flash your input after each query. Okay, no more questions, right? The problem C. I don't know if anyone solved it during the contest here. No. Okay. It seems like a very hard problem, but the solution is really nothing too difficult, I guess. At least if we make a bunch of observations that kind of simplify our life. So we have a bunch of clock hands that are showing some time, and well, the clock hands are ordered by their velocity, how fast they go, and we know that when each clock hand makes its way to the next position, that corresponds to the previous hand making a certain number of revolutions. Okay. So for each time moment, we can determine exactly what are the positions of the clock hands, and we can move the clock hands. That is, if we move a certain hand, then along with that, all the slower hands would move accordingly. So it's like, you know how there are two types of clocks. Once they got like ting, 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 right, every second. And other ones just move very, very gradually. So this clock is of the second type. And when you move a certain clock hand, then all slower hands move with the corresponding rate. And what you have is that you have two time moments that are displayed on this clock, like the actual one that you have and the desired one. And you want to discover what's the total time, what's the smallest distance that you can spend to move some clock hands in either direction, so that to make initial time into the desired time, right? And also different clock hands have different length, so that may depend. Like if we move a clock hand of length 10 by a complete revolution, then the total length that this point would travel would be 2 pi times 10. Okay, basically. Okay, so let's make a couple of observations. And the first observation is that we don't exactly care about the actual time and the desired time, and we only care about their difference, because basically from any particular position, if you wait for a set amount of time, then each clock hand would move forward around the circle by a set angle that only depends on the time you wait. Okay, so that means that it doesn't matter what the actual time is and the desired time is. If you start from time 0 and you want to set the difference, then it would be the same. It would be the same answer. Okay. Should I elaborate on that? Why that holds? Okay. So, and it also doesn't matter if we have the desired time less or larger than the time that we do have, because basically everything is symmetrical, right? We could make time A to the time B, or we could make time B, like time A from the time B, basically by reversing all our operations. So instead of having time moments 0 and B, we are going to set the initial time to absolute value of A and of the difference of A and B, and we want to make 0. You could make it other way, but just for convenience, I'm going to assume that we're going to do that. Okay, so at least you don't it simplifies something. You want to move all the errors to 0 position. Okay. Now let's think about how we should move the clock hands. It could appear that you could move them in arbitrary way, but the thing is, if you consider a particular hand with the set number of positions around the circle, then it only makes sense to move this hand so that it aligns with another position that it could take. And the reason for that is that if we align it somewhere in the middle, like for example between positions, then what we would obtain is basically like the positions of hands that we will obtain will not correspond to any actual time, because we cannot have a time moment where a certain hand is like midway, except if we made it through, because some slower hands moved a little bit. But since the slower hands don't move, if when we move this particular hand, only the slower hands move. So making our hand go midway through a position between two positions, we will obtain an illegal configuration of hands. Okay. So and the thing is, we cannot fix it with moving some other hands as well. Okay. Now it becomes a bit more tractable, because basically for each hand we want to move it an integer amount of positions, either forwards or backwards, and we want to determine what's the smallest total distance. But still, we could have situations where we should move a certain clock hand a very large number of revolutions. So the reason for that is that the clock hands have different length, and if you have a very short hand here and a very large hand here, then it would be more more sensible to move this short hand around and around and around like 100 times, then move this large hand just by an inch. Okay, so we have to deal with that. And how do we deal with that is to get rid of multiple revolutions that we are allowed to have. So we know that if we take a hand and make a full revolution, then the next largest hand will move one position forward, right? And we know what is the exact angle here. Okay. So, and we know the distance that it takes to move a certain hand by one position forward, right? Because for each hand we know its length and we know the number of positions. So what we are going to count is, so for each hand we are going to count the smallest distance that you have to travel in order to move it one position forward, out of all possible ways to do it with this hand or with faster hands. Okay, so in this case, like if there are only two hands, then the answer to what's the smallest distance to move this one position forward is either this distance here, right, or one revolution here. We could go either way, and the result would be the same, right? So for the fastest hand, the only way to move it one position forward is to just move it. For the second hand, we can do options now, and if we have this third hand, we can reuse this answer for the second hand, so that we just repeat this operation a certain amount of times, or we actually move this hand. So if we denote this like Ti, then we have something like, to move the fastest hand, the distance would be something along the lines of 2 pi times the length of the first hand over 60, because we know that the first hand has 60 positions because there are 60 seconds in a minute. Okay. Then for the next hand, we have the smallest time among actually moving the second hand by this length. So this is the angle that corresponds to moving one position forward. Okay. Or if we are not doing that, then we are going to repeat this d1 number of times. Is it d1? Yes. Let me think about that. I think it's rather 60 d1. Okay. So to make a minute hand go one position forward, we have to make a second hand move one position forward 60 times. So that makes sense. And then we write it for the next hand. So it goes something like this. And here we are going to, if we are going to move the previous hand, then we are going to do that d1 times, basically. And so on. So here, when we computed that time, we've actually covered all cases where we move, where we want to move a single hand, like full circle or more. Okay. So now, like if we say that okay, we want to move the second hand a certain amount, and then the minute hand a certain amount, then we may use these times, and we can consider that each hand is not going to be moved full circle, because all the times that it's going to be full circle, it doesn't change its position, except that it does something to the slower hands, and that is going to be covered in our future times. Okay. So now we assume that the time to move a hand one position forward is covered by this, and nothing goes full circle. Okay. Should I elaborate on that? Should I make some examples? Or yeah. Yes, they could. So you could make all hands go both ways, and it could happen that you have a very large amount of time that's almost zero. Then you are allowed to move forward to the actual zeros, because you only care about the positions of hands, not about the actual time. Okay. So now, since we are assuming that nothing goes full circle, and we kind of redefined what the time to move a hand means, then we've defined how we're going to move the hands almost uniquely. Okay, because so we want to make our certain time equal to 0, right? So that all hands point to 0. So okay, so if this is T capital, then we can easily determine the number of, like, the position of the second hand, because it's equal to T modulo 16. Okay, makes sense. So for example, it could be 15. So now, since nothing goes full circle, we're not going to move anything full circle. There are only two ways to make this hand go to 0. It's either we go backwards and make it go like 15 seconds back, or 45 seconds forward, right? And you kind of wanted to make it a shorter distance, but the fact is we don't know which way is optimal, because the time on the slower hands will be dependent on what we do here. Okay, so it could happen that if we go here, then a subsequent hand, which is much longer, will have to make like forward more distance, and that will make our answer an optimal. So we will have to consider both cases. Okay? So, for example, if we go backwards, then okay, so we have fixed the second hand, and it's not going to move anymore when we go to the slower hands, right? So our problem reduces to a slower number of hands, and we are going to assume that basically 60 seconds is the new unit of time, because it's the smallest unit of time that all further hands are concerned with. Okay, so basically we have a problem that is concerned with all the hands from 1 to n, and it has time t. And if you go this way, then what we are reducing it to is a problem that's concerned with hands from second to nth. But if you assume the new unit of time, like the new time estimate here will be t over 60 rounded down. Okay? Because if we had, like, for example, I don't know, 123 minutes and 15 seconds after we've made second 0, then everything else is going to be like the smallest unit of time that we will have after that is going to be a minute. So we can assume that minutes is the new seconds, and we just going to assume that it's 123 seconds now. Okay? So we have reduced to this problem, right? It's one case. It could be an optimal because we could move forward. And if you move forward, we reduce to another problem, because if we are going to make this go 45 seconds forward, then the time that we are going to have is 124 minutes and 0 seconds. Okay, so the second time value that we are going to have is this t over 60 rounded down plus 1. Okay, makes sense? So one of these ways is better than another, and what we're going to do is we are going to repeat this for the next fastest hand, except that the 60 will be replaced with d1. Okay, because it's the new amount of positions on the clock. So we are going to have some branches here and here and here. So basically the problem boils down to deciding the direction for each error so that it minimizes the total distance. Okay, and everything is kind of interconnected. Okay, so it looks like we have a tree of, I don't know, 2 to the 50th possible ways to make a decision. But we can see that here, for example, since these two are adjacent numbers, then, for example, in the middle here, we are certainly going to have an equal position. Okay, so in fact, what we can do is replace this almost backtracking, right? So we can implement it as a backtracking, but we can optimize it with memoization so that it becomes basically dynamic programming. So the only thing that we have to do here is that once we obtain the answer for a certain range of hands and a certain time value, then we don't have to recompute it once again if we need to compute it somewhere else in our tree. Okay, and the thing is, we can prove that if we are allowed to use only these kinds of operations, then we can only have, I think it's at most 2 different time values for each particular range of hands, because basically at all times these are going to be adjacent, and we cannot obtain too many. Is it? Okay, it's probably not 2. But anyway, what we are going to... Yes, 2 is incorrect. 2 is incorrect. But anyway, like if you look at the time positions that occur for a particular range of hands, they are all going to be adjacent times, basically a contiguous range of times. And we can see that this range cannot expand by more than 1 when we go from a range to the next range. So when we apply memoization, the largest amount of states that we can have here is very roughly bounded by n squared. And I think since we cannot have any numbers d equal to 1, then it's even n, but it doesn't matter because n is small, and applying memoization here is very fast. So the simplest way to do here is the simplest way to memorize an answer is to basically construct a map from like a pair of this value and this value to the answer. Okay, so that if you construct a map that you don't care about like the ranges you have in an array, about offsets, so that's very easy and clean and really short code. And here, like when we compute that, okay, we have to move this this hand 15 positions behind. Here is where we use this times t, because t is t for a particular hand is the optimal distance to move it, including all possible ways to use faster hands, basically. Okay, so that's how the solution works. In the end, it's not very complicated. So, yeah, you don't even have to do. You know, it seems like there could be a problem because of the largest time that the clock could display is very large, like 10 to the 300s, but you never care about that because you only care about the difference. And the only thing that you do here is divide and run them. So it's not too bad. Yeah. Let me think here. Not really, and this case is covered by the last the last iteration of our backtracking, and that's it. When we've exhausted all our clock hands here, then what we get in the end here is usually 0. Like, so if we, for example, there is a single hand. Okay, let's consider the case of a single hand. So we could have 59 here, and we want to go to 0, right? So in our case analysis here, we either go 59 forward or 59 backwards or 1 forwards, right? And if we plug that in our formulas, we'll arrive at the case where we have no hands, but we have to display 1. And that one corresponds to the fact that we are actually displaying something like 1 minute later than we would actually do, but we don't exactly care about that because like every 60 seconds everything looks the same. So when we go to our last layer of dynamic programming, we obtain some number here, but regardless of that, we have obtained the correct position. Okay? So you want to think about what happens when we go from 59 to 0. Okay? It will still be covered, basically. I think it's 59. Yeah, the thing is, I don't actually care about the maximum. So it's just the absolute value here. It could be that, like, I mean, if there is a single hand and it goes 60 seconds, we like someone can ask us to display 1,000,000 seconds, right? And we don't even take that modulus 60, so that still works. We don't care about the number of complete revolutions because basically we only care about stuff modulo our numbers here. It's probably the best I can explain it. Maybe you can try and work out some cases for yourself. It's probably a good idea. Okay. Any more questions about that problem? Okay. The problem D. The problem D was about moving through some traffic jams. And so basically you were standing at a particular point in the city and you had several rectangles that did not intersect, so that if you move within a rectangle, then you move slower, and you are only allowed to move like horizontally or vertically by unit transitions. And you are like in each rectangle, for example, in this rectangle it could be 17 time units per 1 square. In another rectangle it could be another time, but moving outside the rectangles and moving on the border takes always like 10 units of time. And you want to determine what is the shortest time it could take to get from point A to point B, basically. Okay? So the coordinates were pretty large. The coordinates could go up to 10 to the 8th. So this is obviously a graph problem, right? Well, you can represent it as a graph problem because there are vertices and there are edges, and each edge takes a particular amount of time. But we can't exactly represent all possible points, so we're going to compress some stuff up. Basically, the thing is, you always want to stay on particular lines. So let's do something. So let's consider all points and also all vertical borders of all rectangles, and draw a vertical line here through all of them, and also do the same in the horizontal direction. So something like this. So we've cut our plane into a bunch of rectangles, and we can see that now each rectangle has like either it's a gem with a particular time, or it's not a gem. Okay. So now we want to say that we only want to move along these lines, and the reason for that is that if you want to travel some other way through the rectangle, like move around, I don't know, and arrive at some particular border there of the rectangle, then you can always make the same way or better by using the borders, like the lines, right? So for example, you could go like this, and it wouldn't be worse. So you can always, there is always an optimal path that goes along the lines. Okay? So since we have at most 1000 rectangles, then the number of lines in each direction is at most 2002. I'm going to say 2000 for clear. So that means that since we're moving along the lines, then we only care about the vertices and the intersections. So we have at most 4 million vertices. Okay, and so these are the vertices of our new graph. And now there are some edges, and we want to determine their length. But we can do that just by considering all rectangles, and then basically for each rectangle we want to consider the borders within the rectangle, so that, for example, we know that this border is inside the rectangle, so we should make it longer accordingly, because we know the time to move the unit here, and we also know the distance between consecutive lines. Okay, basically the way you construct these lines is you take, for example, all x's that are present in your input, sort them, and then delete the equal values, and then there you have your lines here. Okay, and the same for y's. So now we have this number of vertices. We have pretty much okay, let's see. We have at most 8 million, I think, edges, because either an edge is vertical and then it has a unique lowest point, or it's horizontal and then it has a unique left point. So now we have the graph that has these much vertices, these much edges, and we want to find a shortest path there. Okay, and we know that the edges are weighted. So what one wants to do is to run a Dijkstra algorithm on that and say, okay, we're done, right? The thing is, I believe, like, I'm not saying it's impossible to get this accepted, but it's really, really hard. And the reason for that is, like you know, the Dijkstra with priority queue works in log n time, right? So if you multiply this number, and it's actually twice this number because the edges have both directions, and you have to multiply it by the logarithm here, which is roughly 20. So you have something along the lines of 300 million. And to make it worse, you need a lot of memory. Like you need basically this much memory times the number of bytes to represent some data. So I think like it's very hard to meet both constraints here, the time and the memory. And the thing is, for the purpose of this problem, you can do better than the Dijkstra algorithm. And I believe someone still got this accepted, the Dijkstra algorithm with some optimization. It could be. I didn't pay. Like, I didn't study the code, but I believe the time it took to work for one particular solution that someone got today accepted was, I believe the time limit was 2 seconds, and the displayed running time was 1.996. Very close. Nevertheless, let's discuss a faster solution. And a faster solution is, it uses the fact that the rectangles that we have do not intersect. And this is important because if this condition holds, then we can make certain assertions about how the optimal path looks. And the one assertion that we want to make is that, okay, so we have target points, we have rectangles, something happens. So the assertion is there exists an optimal path so that at least one of the coordinates is monotonous. So basically, either x changes monotonously so that it, for example, it does not decrease. So here we can consider like something like this path, or here we may want to travel through the traffic, and here we arrive at the final point. Okay, so either that happens in an optimal answer, or it happens to the y coordinate. Okay, because we could have it the other way around. Like, if I had just 30 seconds to prove it, I would say that it's like you cannot make you can travel between the rectangles. You cannot make it so that you have to make these U-turns in both directions. If I were to do a rigorous proof, I would probably not go for it. But the idea is, I mean, one idea that you could use to kind of prove it is, I was thinking about induction by the number of rectangles. So if we have no rectangles, then obviously our optimal path is like this, and it's monotonous in both coordinates. So okay, if we have a certain rectangle, so assume it's true for all n, and then we consider n plus 1. So we have a bunch of rectangles, a bunch of rectangles, a bunch of rectangles. And now we want to, okay, so now let's look at a certain optimal path. And let's look at the first abstraction that it meets, okay? So for example, it meets this rectangle, and there are only so much ways to get around the rectangles, right? So either we go through it, or we want to get around it, so we do something like this, right? So in either cases, we still have monotonicity by at least one coordinate, because it could happen that we would choose to go like upwards and make another U-turn here. So, okay, now let's try and think about what happens to the other part of path. Like, what is the next direction that we would choose to go? Okay, so can we go left? Probably not, because it doesn't make too much of an optimal path, right? So we can go left. Okay, if we choose to go right, then we may as well treat the rest of the path as just an optimal path from this point to the finish point without this rectangle. Okay, so if we delete this rectangle and start with this point, we can apply our induction hypothesis. And so, yeah, so for our induction hypothesis was that at least one coordinate is monotonous. So let's consider the rest of the path here. So either x is non-decreasing, in which case we are done, right? Okay, if x is not increasing, then we did something very stupid, basically, right? Okay, another two cases is when y is non-decreasing or y is non-increasing. So if y is non-decreasing, so after that we do something like this, then we kind of did not very good job of getting around the rectangle here, because we could go something like this. Okay, so for any way to continue, we could make it around the rectangle the other way, so that we would continue. I'm not going to a lot of special cases here and a lot of details, but you can probably get the idea, right? So here we can make around the rectangle the other way, and if we're going down, then okay, if we've arrived here, then why did we do that? Because we're going to go down afterwards. So we have to assume that we are at the lowest point, and in this case our assertion still works. Okay, so that's kind of a hand-wavy way to prove that. Anyway, so if you assume that's true, what we're going to do is to basically say, okay, so we know that the optimal path has to be monotonous in at least one coordinate. Okay, so let's try an optimal way that's monotonous in x coordinate, for example. And that makes our problem much simpler. So we want to get from here to here in presence of rectangles. And basically we are going to keep our original graph, except that now that we know that x coordinate is non-decreasing, then we can safely go from left to right. We could not do it in the Dijkstra algorithm because in general cases the path could look like anything, right? But here what we are going to do is we have so for each of our lines here we had a bunch of points. So we want to move our line gradually and basically recompute the shortest distance to every point here. Okay, so we start at a particular point, and we know that the distance here is 0, and for all the other distances we basically go upwards and try to improve the next distance by basically if this length is 100, so here we have infinity for a start, then we know that here we can obtain the distance 100. Okay, so trying to relax all distances by all the ways going down takes only a single traverse from bottom to down and relaxing the next distance. Okay. So this way we have obtained optimal distances if we're only allowed to go up. Since we can go down, we do the same thing from the other direction. Okay. So this way we have solved kind of one-dimensional problem, right? Like if you're only allowed to move up or down and we know the edge length, then this is the way to go. Now we have to move to the next line. So what we are doing is we are taking these distances here, and when we move to the right, we have to move to the right. So to each number here, we should add the weight that corresponds to this particular horizontal edge. Okay? So we obtain some distances here, and then we have to do the same thing as we did here. That is, we should try and see if there is a way to make some of the distances here better by going up or down, which is basically the same thing, right? So we do that until we reach the finish point, and since we've assumed that the path is going to be monotonous in X, then the distance that we're going to have here is the optimal answer among X monotonous path. Okay? Makes sense? So here we are not basically doing, we're not using sets, we're only using arrays, and that means that this works in the total number of points, which is just this number, so without any logarithm. And then we have to do that for y monotonicity, which is just the same thing with all coordinates swapped. Okay? So, yeah, I guess this observation was not too easy to make, because it looks like the rectangles can be arranged in ways so that the path is nesty. But even if you come up with this, like with this assumption, and you're not sure how to prove that, you can try and stress test it. Like, if there is an assumption that you are having hard time proving, but you strongly suspect that it's true, and assuming that you do not have like a bit of, if you don't have a lot of use for computer time at the moment, for example, you solved everything else, then you can spend like 15 or 20 minutes and just write down some small solutions that use that and check if it holds on many random tests. This is a good way to prove something during the contest. It's not like it's something illegal. It can fail sometimes, but you may still as well do that. Okay, so now this solution seems to work, and it works pretty fast. Are there any questions about the problem? Like, this is one of the hardest problems in the contest, so don't feel bad if you didn't solve it. The problem E, did anyone actually read it? Okay, did you understand it? No. Yeah, so it's basically a bunch of nonsense about concurrency computation. So it may take quite a bit of time to get through the statement and understand what it does, but I'm going to tell you what it's all about in the end. So to simplify, we are basically having two algorithms that are running parallelly, and what do we mean by running parallelly is that if they are making some operations, we cannot predict which order they are making. So for example, if you have instruction 1, instruction 2, instruction 3 for a first processor, and like some instructions for the second processor, and they are performing them from the top, it could be that one processor is for some reason faster than the other or slower. We can't exactly predict that. It could have some other stuff to do. So we are going to assume that our operations are performed in arbitrary order. So basically, each time frame, one of the processors is going to perform one of the instructions. So it could be that they change turns and perform instructions like first 1, 1, then 2, 2. Or it could go that the first processor does all the work, but then the second processor wakes up and does all his work. Okay, so we cannot predict that. And we are considering the situation where these processors have shared memory, so that in this particular problem there are three variables A, B, and C, which are initially zeros. So you can see that since these are shared and processors can perform stuff in different order, it may very well depend on like what actually happens on the order of what happens here. Like if someone goes where he's not supposed to go, he could spoil some memory, and then this would break everything, destroy the computer literally. So here we are assuming that, so okay, what these programs are, what's the set of instructions? The set of instructions basically contains instructions. One instruction is basically if, it's called test. So the instruction test does basically look at the variable, for example, a or b or c, and look at its value, and the values of variable can only be 0 and 1. So if the variable is set to 0, then you have to then you go to the line and 0. Otherwise, you go to the line and 1. Okay, so this is just basically an if and a bunch of gotos, which you shouldn't use, by the way. Another instruction is set, which is basically write 0 or 1 to a particular variable. And so you can see that with this you can implement like loops and conditions and all sorts of stuff, right? But there are two special instructions. One is called NCS and the other one is CS, which really does nothing, but we assume that the NCS corresponds to some code that like the processor does with his own memory. So this is basically a safe operation, and when the processor doing this, it does not tamper with the other processor in any way. Okay, and the CS is the opposite. It's the dangerous section, so that if one processor is doing CS and the other processor also wants to do CS, that it can be a problem. It is very bad. We don't want to have that at all. So we are considering this. So basically, CS corresponds to important work that you have to do basically indefinitely. So, for example, you can imagine that there are two processors and I don't know, they are waiting. For example, you have a web server and you have to check like many times per second that, okay, do you have a query that you have to process? So you want the checks to occur as frequently as possible, or at least sometimes, but you don't want for the both processors go for the same instruction, because that would spoil something. So that's what CS does. Okay, so now we have these two algorithms, and we are going to assume that they are running in any way possible. So each processor has its set of instructions, and it has two pointers, and then we are going to assume that the parallel thing happens. That is, each processor may perform the next instruction, exactly one, and we cannot predict the order at all. So we want to kind of, given these programs, we want to make some safety checks, which is to verify that our algorithms satisfy a bunch of conditions. The first of these is mutual exclusion, as it's named here, which is basically the processors cannot both execute CS at the same time, the critical section, which is basically like the safety condition. Okay, and that is going. This has to hold with regard to any possible history of how the processors do work. Okay, so that's one property here. Another property is deadlock freedom. So deadlock freedom says that it cannot happen that if we are running indefinitely, there is some point after which we are not doing any critical sections. Okay, so that means that basically our our algorithms have stopped like doing any actual work. They're just abstracting each other from coming forward. And the last condition is starvation freedom, which says that basically, so okay, actually if you consider any history, which is the way the processors do their instructions, it may, if you consider the infinite history, then it may happen that either both processors do infinite number of steps, right? Or it's just one and the other one does finite number of steps and then it stops. Okay? So the starvation freedom says that in any history, if a thread does infinitely many steps, it also executes CS infinite number of times. Okay? So if both of them do infinite steps, then both of them do CS infinite number of times. If it's only one, then it's only one. Okay, so that's a lot of information about concurrency programming, and it probably does not have anything to do with any actual concurrency programming, but never mind. So after we've kind of worked out what does any of that means, we're going to reduce our problem to something that actually makes sense, which is we are going to consider like all possible states and all possible ways to go between them. So what does describe a state? Basically, a state is of the current program is described only by like the line here, the line where the instruction pointer is here, where it's here, right? So L1, L2, and also what are the states of variables here. Okay, so we know that each program has up to 9 lines, so there are at most 9 times 9 times 8 here. I think it's about like less than 700 different states, right? And now, so if you are in a state, then there are basically 2 ways what could happen next. Either we move a pointer here, or we move a pointer here, and in the meantime, it could happen that we change one of these variables. So there are 2 different states that we could go to next. Okay. So what we have here is a graph, a directed graph with like vertices here and edges, directed edges, and now every history, which is what is going to happen in our algorithms, is basically simply a path in our graph, starting from an initial state. Okay, and now we are going to translate all these properties in terms of what happens to the graph. Okay, so in the mutual exclusion property, you cannot have that both of the algorithms have their instruction pointers pointing to CS. Okay, so there is no way to reach a state where this happens. And this is basically easy to check, because if you have these states and if you have constructed the graph, which is to construct the graph, you basically have to go into this state and then look at a particular line and then maybe change the variables. So not too hard. Basically just have to look at what happens. So to make sure this does not happen means that you have to start at the initial state and then check that no state that has both instruction pointers pointing to CS is reachable from the initial state, okay, by following anything. And that can be done just by running a DFS on this graph. Okay, so that's an easy one. Next ones are a bit harder. So the deadlock freedom, it means that there is no path. Basically, in any path that we should follow here, there are infinitely many executions of CS. So that means that there is no path in our graph that has only finitely many executions of this of CS. And what that means, basically, if we have an infinite path, then the states are bound to repeat after a certain amount of time. So if you consider a particular path of this type, right? So we follow something, and then after a certain point, no CS occurs. So that means that we have reached a state that we can also return to, so that this portion of the path have no CS. That's CS on this path is not performed by any of the processors. Okay? So if there is a reachable state that lies on a cycle that does not contain any executions of CS, then that means we're good. Okay? So to do that, okay, so we already know which states are reachable, right? Because we've run the DFS on the first to determine this. So the only thing we have to do is to check for every point, is there a cycle that goes through it that contains no CS? And to do that, what we basically are going to do is we forbid all the edges that say perform CS, and then we are going to find like all basically all vertices that lie on any cycles. And that can be done with some DFSs as well. And it can be done in linear time, but since the number of vertices and edges in our graph is less than 2000, you can run DFS from any vertex, basically. So you don't have to be too efficient about it. Okay? The last one is that okay, so any so yeah, in any history, if a thread executes infinitely many steps, it executes infinitely many CSs, basically. So let's try to think what that means. Basically, once again, in infinite history, some states are bound to repeat. So we only care about what happens in some cycle that contains a reachable vertex. So if, let's assume that, for example, the first thread makes an infinite number of steps. So on these cycles, there has to be at least one edge that is like first processor does something. Okay? Since we are going to repeat this cycle infinite number of times. But all of these edges, so all of these edges that first processor does something have to be no CS. Okay? So if we have this cycle, then we violate this condition. Okay? We perform infinite number of steps by the first processor, but it does no CS. So we want to look for these cycles. And it looks kind of complicated, but we are going to do basically the same thing, except, so we are looking for a cycle that has at least one edge of this kind and no CS. So basically, again, we are going to, first we erase all the edges that contain CS. And now for each vertex, we want to find if there is a cycle that has at least one number 1. And the way we do that is that we can construct a new graph where we have a state plus a number that's either 0 and 1. And that is, on the path to this vertex, did we visit at least one number 1? Okay, so if we have a state here, then to find a cycle of this kind in the new graph, we have to find the path from the state that starts with 0 to the state that starts with 1. And here we have no CS. Okay? And so we did it for the first processor, and we also do this for the second one. And yeah, the last important thing that I already said is that we only want to do this for the states that are actually reachable from the initial one. Because if it's unreachable, then it never happens. And we don't care about that. So this problem was about reading and then translating everything into graph theory language, and then it becomes kind of feasible. Okay, are there any questions? If you're thinking of a question, why did they include this problem here? I don't answer to that. And there are also there is another page of samples. Interesting. Okay. So the problem F was about Fibonacci number system, which is we can uniquely write numbers as sums of Fibonacci numbers, of distinct Fibonacci numbers, and with additional restriction that no two adjacent Fibonacci numbers are used. And it turns out that there is a unique way to do that. So now we have these representations as strings. We've concatenated all of them. And then we want to know how many ones there are in a certain prefix. Okay. So we have a bunch of representations here, like 1, then 1, 0, then 1, 0, 0, and 1, 0, 1, something like that. Okay? So, and we know the length of the prefix. The first thing that we would probably like to know is how many complete representations of numbers do actually fit within the prefix of this length. Okay? So if we do that, then what we do next is we will probably deal with summing the ones here, and then we will have to take the next number represented in the Fibonacci system, and then count the number of ones in this part. And that's basically all we do. So the problem is how do we count the number of numbers here? And there are a lot of ways to do that. Basically, to start, we are going to find out what is the number of numbers of each length. And I think it's Fibonacci numbers. So there is one number of length 1, one number of length 2, two numbers of length 3, here and here. Then it follows 3 numbers of length 4. So at least we know that. Right? And then if we have n, then so yeah, this is easy to compute. Now we consider length by increasing, and we know that we have already some prefix of length p, and we know that what follows is like k numbers of length l. So this is the total length of the new numbers, and this has to be at most n if you're going to include all these numbers. And if that holds, then we go to the next length. Otherwise, we take the distance to n here, and then divide it by l, round it down, and that's how we know the number of numbers that fit. Okay? So that's how we determine the prefix. And then we have to count the total number of ones there. And okay. Okay. So one way to do that is to see that basically we want to do that by groups. Okay. So consider a group of numbers that have length l. Then we see that they start with 1, they continue with 0, and then what follows is a string of length l minus 1, which does not have any repetition. So this is basically our sequence, except we allow leading zeros. Okay, and we can write down some recurrence relations to determine the number of these numbers and also the number of ones there, which is basically like okay. So let's write down the relations for the numbers, which is going to be again Fibonacci numbers, I assume. The reason for that is that so we consider this number and we don't care about leading zeros. So either it starts with a 0 and everything else is a good string of length L-1, or it starts with 1, then it must be 0, and then it's any string of length L-2. Okay, so that's why this relation here. C is the number of all possible strings. And now we want to count the number of ones in all the strings of length L. And that is basically the number of ones in all the strings of length L-1, because here we just use them all and just introduce a new 0. Okay, and here, so all the strings that of length L-2 go here as well. But then for each of them we are going to introduce a new one. So we are going to add the number of the strings. Okay, makes sense. So this is how we compute the total number of ones in all of these strings, and we can use this to obtain the total number of ones in each of the groups, except for the last. Okay, and basically for the last one, we are going to use some recursion. So we have all the strings of length like L, right? And we only want to know the number of ones in some prefix of that. But we know that first all the strings that go here start with 0. Yeah, we had 1 0 before that, but it's easy to just drop it and consider all the rest. And all the rest start with 1. So it either happens that we that we don't care. So our prefix, there are two cases, right? Either our prefix contains only numbers that start with zeros, in which case we can just decrease L, okay, because we don't use zeros, or our prefix goes beyond the zeros and goes into ones, in which case we can use our previously obtained number for this group of zeros for all numbers that starts with zeros, and then go into ones, but we know that these numbers start with 1 0, so we cut them off, add these ones to our answer, and then basically reduce the problem to the prefix this large and the length too shorter than before. Okay. Maybe was it too fast? Is this okay? It's a general idea. I think the details here should not be too hard. I mean, the main thing is, the first thing is these relations, because we are going to use them, and then it's like, you know that you have to reduce the smaller cases here, and you want to take care of all ones that you have. So I guess that's all I want to say about this problem. Are there any questions? Okay. The problem G, you had a bunch of monitor types and you wanted to be a large rectangle of them, and you had some lower bounds on the total size of the rectangle, and you knew the price for a single monitor, and you wanted to find the cheapest way to construct them. And it's basically try everything and determine the number of repetition by each dimension, and then multiply the price by the number and take the minimal amount, which I believe most people were able to do. So are there any questions about G? Okay. The problem H was an easy one, but maybe the idea is somewhat elusive, I think, in here. I was participating in the contest as well, and I remember not being able to come up with the idea. But luckily, one of my teammates did. So anyway, so we had a bunch of numbers AI, and we know that for each number AI, it's within 1 and I. And what we want to do is we want to take the sum of these numbers, except some of them with the plus sign and some of them with minus sign, so that the sum of these numbers with signs is 0. Okay. Or maybe you're not able to do that. For example, if you can see that if like the sum of these numbers without caring about the signs is odd, then the parity does not depend on the signs. So if it's odd, then there's no way you would obtain 0. Okay? And if it's even, turns out that the answer always exists. And the reason why it the way we obtain the answer, we prove the answer by actually presenting an algorithm to obtain it. So we start from considering an. Okay? And we might as well take it with a plus sign. So now our sum is equal to an. Okay. And what we know is that the modulo of S is at most n at this point. No, obviously, because an does not exceed n. And basically our invariant, so we are going to consider numbers in this order from nth to the first, and we are going to take to choose the sign on the spot for a subsequent number, and we want to make it so that the absolute value of the sum when we are considering if ith number is at most I. Okay. So, and it turns out that we can actually do it every time. So if this is satisfied for I, then for the next number, there's always a way to choose sign for this number, and this sign actually should be opposite to the sign of S. Okay, so you can see that if you do this, then this condition is going to be satisfied at every point. Should I go into explaining this? No? Maybe? Please do not be afraid to ask me to explain something. Should I? Well, so basically we know that our difference, our sum after the ith number is somewhere here. So what happens when we choose the sign for this number ai is that I goes to 1, I minus 1 goes to 0, and then all the way. When we have 1, then we have something along the lines of minus I minus 1, and then for 0 we have minus I minus 2. So the largest absolute value is here. And for all the other numbers we are going to add, so for minus 1 we are going to have I minus 2, and it decreases until at minus I we have minus 1. So out of all these numbers, largest value occurs here, and it is, well, largest absolute value, and well, it doesn't exceed I minus 1. So basically that's how it goes. So after considering the first number, we have that S does not exceed 1, and since we know that S is even, that means like there's the only even number that satisfies this, and this number is 0. And if the sum were odd, then this would be either 1 or minus 1. So if you don't want to check the parity, you may implement this algorithm and check that you have 0 at the end. It doesn't matter too much. Are there any questions? Okay. In the problem I, you had to parse some variables and ampersands and stars and square brackets, and then rearrange them in some order. Basically, there's not too much to this problem, except for you had to read the input, and not to reverse the left square bracket with the right square bracket. I bet that some of you did that at the first try. I know that I would have done it, probably. Maybe there are maybe any of you have questions about how to better read stuff, or I have a language that is not able to do things. Everyone made it? Okay. In the problem J, you had a string, you had a bunch of words, and you know that at the start each word had vowels and consonants alternating, and then someone applied a simple substitution cipher to it, so that the letters were rearranged so that equal letters become equal, but equal letters remained equal, but different remain different. And you want to check if it's possible to decipher the text, basically, so that the letters still alternate. Okay. So, first of all, if we consider any way of, if we consider any cipher, then we can notice that it doesn't exactly matter which letter is mapped to which, as long as it's a vowel. So, for example, if we have a map that A is mapped to A, and B is mapped to E, and C is mapped to, I don't know, G, and if it's a correct decipher, then we might as well write E here and A here, and nothing would change, right? Because we only care about that vowels and consonants alternate. Okay, makes sense. So it follows that we only have to choose which of the numbers, which of the letters are mapped to vowels and which are mapped to consonants, and then after that we check that the deciphering is correct. Okay. So first of all, how many ways are there to choose some letters out of 26 that will go to vowels, and all the others are obviously going to be consonants. This number is a binomial coefficient 26 choose 4, and I think it's less than 100,000. So we can just try all that. But the problem is, after we have done that, we could try to decipher the text and check it if it's correct, but the text is very long, so we are going to be faster than that. And to do that, we are going to basically remember which letters are adjacent in any way of the text. Okay, so for letter A and a letter B, we are going to remember if there are any place in the string where they are adjacent. So basically, we want to construct a graph on letters, so that an edge between two letters means that they occur together in some place of the text. Okay, and now we have this graph, and if we have chosen 5 letters to be vowels and others to be consonants, then what we should check is that there are no edges between the vowels, and there are no edges between the consonants. Okay, so this we may pretty much do explicitly, because we have the graph, and the graph has only 26 vertices. So we may as well do that just explicitly without thinking. And so this takes about 26 squared operations for every way of doing this. Okay. So, are there any questions about J? Okay. Okay, the problem K was about introducing some abbreviations in the text, and basically an abbreviation is we replace a sequence of words with their first letters, and we want it to be unambiguous, so that there is basically a single way to to map out a single of words that occurs in the text that has this abbreviation, and also the abbreviation cannot appear in the text itself as a word. So these are the rules. And there are some rules how we later apply this abbreviation to shorter some sequences. So we want to choose one with the highest effectiveness. Okay. So this is not too hard to do. There are a lot of wrong assumptions that you could make while solving this problem, but let's try to do it safely. So if you do it safely, what we basically want to do is we have a sequence of words, and we are going to try any contiguous sequence of words here, and try and see if this is a good abbreviation, and if so, what is its effectiveness. I'm sorry. So to do that, we want to count basically for this sequence of words, does any other sequence of words has this abbreviation that's different from this one, and also how many times it occurs here. One way to do that would be to construct something that's called a try, and it's just one way. I believe you can go with a simpler solution, but this is going to be n squared without any logarithms. I don't know if any logarithms are allowed to pass. So basically, we are constructing a tree so that so that there is a single letter that's written on each particular edge. There are no two edges with the same letter leaving the same vertex, and each sequence of each path here from the root corresponds to an abbreviation that we could have here. Okay. So now, first we construct this try, and this is basically by considering all subsegments, and we can construct it in time of n squared, where n is the total number of letters. So we are going to need some additional information about that, and that is basically for each possible abbreviation, we want to know if there is a unique sequence of words that corresponds to that, because that's important. So what we are going to do is that at each vertex we are going to store basically the sequence of words. Okay, so we're going to store the sequence of words, and well, either that or the fact that it is already unambiguous. It is already ambiguous, so there are some differences. And to do that, basically, when we first create the vertex, we put the sequence of words here, and then every time we take another sequence of words and we take the same path, we compare the sequences here, and either they are different, which makes this vertex ambiguous, so we mark it somewhere, or otherwise they are the same, in which case we say that, okay, there is one more occurrence here. Okay, and also for each word here, we have to check if it's an abbreviation, and if it's abbreviation, then we have to go down and say, okay, you're out. Basically, you cannot do that. And after that, you can go to each particular abbreviation that's possible, look at the length here, look at the number of words, and that's enough to compute the effectiveness. The only issue with that is if you store these sequences of words, then it could happen that their total size for all the vertices here, since there could be n squared, it would be this sequence could be of length n, so it could be n cubed total memory. So instead of these sequences, we will store their hashes. And also length, because we have to use it to compute effectiveness. I would like to say that, like, I would really like to say that there's a better solution, but I don't think there's one. Literally, every jury solution that I looked at had hashes in them. Yeah. Yes, of the whole sequence, exactly. So hash is basically any function that takes words and returns numbers in a consistent pseudo-random way. And the important thing here is that there are like about n squared different sequences, so that to effectively avoid collisions, you want to make the range of your hashes strictly greater than n to the fourth. So you probably want to use long. If your range is too small, you are prone to collisions due to the birthday paradox, which is basically if you have square root of n numbers from 1 to n, then with high probability some of them they will be equal. And basically that's it about the problem. You shouldn't be too there are special characters. I mean, you mean 13 and 10? Or... Yeah, so you also had to be careful about how you read stuff, which is basically the thing that I did was using cin to parse different tokens that are separated by spaces and line breaks. And then in each token you go from left to right and basically construct words, because there could be more than one words. I mean, basically according to the statement, every character that is not a letter is a space. So you have to pay attention to that. Okay, I think that's it for today's contest. As I said, it was considerably harder than the yesterday one, or the day before yesterday, actually. But I think you still did a pretty good job, and I participated in that as well, so it wasn't too bad. Yeah. I think like the current preferences are you can see the code if you have solved the problem already. Oh, maybe for this contest I forgot to enable it, but for you mean like in the standings you click and it doesn't work? I've asked Mike about that a few days ago. Maybe I can just enable like the common list of submissions, so that everyone sees everyone, despite not solving something. I think that would be the simplest. I think I'll do that. Okay.